such that this becomes rank 2. And what we hope is we construct this such that this can approximate. So I'm drawing this means originally it's maybe far away, but you know it kind of converges. So this is a very hand-waving notation. So converges to the inverse of the Hessian, okay, at some point. So C is some point between xk and xk plus 1. And all the constructions relies on the following fact, okay, which is the Newton method. We use a quadratic function to approximate our optimization, this target function, and that is let me directly write on my let me still write on this. So this is what we hope we would like to achieve. This is what we hope, and we use this actually to derive what is U, what is V. Okay. So this is this guy. So delta G is the difference in gradient and delta x is a difference in x. I think in the textbook, Nocito and Stephen Wright, they use S, so they use SK to denote this and YK to denote this, but so different people like to use different notations. So I follow this Trondheim's notation, and this is so if we have learned physics, the modern development of physics since the 19th century, so they introduced a new method to describe something like Newton's second law. Okay. So what they introduced is called Hamiltonian. So Hamiltonian is about duality. Here is the same. Okay. So what happens is we consider not only this equation, because this equation relies on the fact that, okay, so this equation is basically an approximation to this. Okay. So now what happens is we can create and update a rule such that we take advantage of what we called the duality okay. So such that we keep, this is let me put it in this way. So we use this duality, but implicitly. Okay. So this is the hidden duality we can exploit. We have only exploited this equation in the DIP update. Okay. We haven't. we haven't explored this relation, okay, which so this can give us actually more information on the curvature of this whole, like this whole this objective function. All right. To think why this makes sense, we can use a simple quadratic function to think about. So BFGS looks like this. So we have, okay, for example, so this is our objective function. So what quasi-Newton does is, so Newton is at each point, okay? We approximate each point by a quadratic function. So this is what Newton does. What quasi-Newton does is, instead of constructing a quadratic approximation at each iteration, for example, then we apply the gradient descent, or stiffest descent for this quadratic approximation. It constructs gradually sharper and sharper quadratic approximation. For example, if this is x1, this is x2, this will be our x3. So quadratic sharper and sharper, estimate. And BFGS is, we not only use the curvature information of f, okay? So the curvature information of f is f's second derivative. So how curved, this thing is, all right? So this is a very natural intuition in optimization, is because the more curved, okay, so especially for non-convex function, right? So for example, here, it's kind of curved, right? Especially for the curved part, we have to slow down, otherwise we kind of overshoot. So this is the intuition, but there is another consideration, that is, sometimes, okay, so for the more curved part, it may not even be positive. So the idea is we correct so that we kind of include, so we kind of always use a positive. So this is the intuition. So for example, here, okay, so at this point, the quadratic approximation will look like this. This is our wanted. So the BFGS said, okay, so what if this is not true, is we kind of construct the inverse of this function. I don't know how to draw, but locally, so that it kind of, creates some sort of envelope, so that yeah, we will see this in the numerical example when we see illustration.
Excuse me. You were standing in the way while drawing. Can you repeat it, please, again?
Okay. So, Newton method for this general, arbitrary non-convex function is at each point. My bad. Yeah. So at each point, we use a quadratic function to approximate this. Okay. So quasi-Newton idea is, so we use a quadratic function to approximate this f at each iteration, then we can apply gradient descent for this quadratic function, which we spend the first half of our semester learn how to optimize a quadratic function, which is already quite complicated and dimension. So Quasi-Newton says, okay, so I don't approximate this quadratic function in one shot because the curvature information here is kind of unknown, okay? So curvature, just what I mean by curvature is, sorry. So we can roughly understand the second derivative as curvature. It kind of describes this type of sharp turn, okay? Because the bigger the second derivative is, the sharper the turn is, okay? So this is the intuition of how the method is developed. I mean, so if we are doing mathematical research, I mean, of course, deriving the formula is important. It's like a basic skill, but intuition is more important when we already have the skill. So quasi-Newton is we construct a sequence of things, okay, that approximates the curvature information. So we don't do it in one shot, but we gradually make our curvature more accurate. All right. So, and suddenly this process becomes more cheaper, but there's a drawback, that is, so what if the function looked like this? So if the function looked like this, you know, we're good locally. But if the function suddenly has a bump, oh, then we're in trouble, okay? Because the quadratic approximation around this neighborhood will look like this. So we're not doing any like a descent. All right. So what we do is we kind of correct it using its inverse, using the Hessian inverse. Think about the Hessian inverse is like we create, yeah, maybe this will go too deep. So locally we create what we call a Legendre transform. So it convexifies things, okay? So it looks like, it will look like, kind of like this. So at this point, even though, you know, the traditional quadratic approximation will look like this.
Excuse me. If our function has lots of these bound points in it, kind of like inversing like multiple times, does it make our like expensive?
We're not inverting. In computation, we're not inverting.
Because like you said, like if we kind of like reach that point, we will inverse the Hessian like.
Yes, but the key point of quasi-Newton is we never invert the Hessian. We create a sequence of approximation to this inverse. Yeah. So then, last time we proved the theorem, okay, so which is S and W formula. Let me write down here. That is. So the top can be also written as, so now what we want to use today is actually a special case of it. It's actually a special case of it. That is, we let so today's special case special cases is we assume A is symmetric, which we have shown. Rank 2 update will maintain symmetry and also positive definiteness.
Can you write limit any other?
We can't see.
Okay. Sorry. So today, because we do this one twice, so let's reserve it this for. So what today we're gonna do is A is A transpose, and we get a U equals alpha inverse B, so we will have is A plus alpha inverse B. Tensor product with this inverse is A inverse minus, so alpha is in front, now we have this is A inverse U, tensor product with A inverse B, and this is 1 plus alpha inverse A inverse U B, but normally what, let me use a new line, but normally so this is a formula we will use is, so we multiply alpha in front.
In the left side, there is A, so it will be M inverse. In the left side, the second equation.
Okay. So in rank 2 update, we kind of learned this formula. So this is the FP. So this is rank 2 update. And the duality is this. Okay. The duality is we switch every delta G to delta X. And we switch every H to B.
Is that U into alpha A plus alpha inverse U into V? Is it V?
Which line?
Okay, I got it.
On the numerator.
Yeah. I got it.
Oh, okay. My bad. You're right. So everything here should be V.
Yeah,
Sorry.
that's what
Sorry,
I was
sorry.
thinking.
Yeah. sorry, this is, let me say, this is the formula we want to use today, okay?
We changed the V, right? U, sorry, we changed the U.
Yeah, we replace U to be alpha inverse B, so every U is, this is a formula we want to use, sorry.
On the duality on the first fraction, should that be a BK, not HK on the bottom?
Yes. So what we're going to do is we're going to make several notification, simplification, and then we'll derive, okay? So then we'll derive. So what we want to do is we use duality. Okay. So goal today is we use duality and the Sherman, Morrison, Rubery, okay, to get a new update rule. So this is what we're going to do. To do this, we're going to make several notation simplification. Okay. Otherwise, it's too long, too complicated. And so if we simply denote delta x as delta, I mean, because each time we're talking about, this is not like CG, you know. This is not a conjugate gradient that we need to talk about, you know, 2 consecutive iterations. And we only talk about 1 consecutive iteration, so we can use this simplification. Sorry. And moreover, we make use of this simplification as well. So we denote, we use denote. So we denote. So in case some of you are not from math, this column equal just means we denote, you know, this b sub k. Okay. So and we denote h sub k as h and bk plus 1 as b plus, and we denote h k plus 1 as h plus. Okay. And then we can write this rule. So rule number b. So we want to write rule number b. So so let me add one more line here is we want the bk to be gradually better approximation for the Hessian. So the rule number b is, so I want to write all right. So first we rewrite the update rule as follows. So it will greatly simplify our life. Okay. Which is like this. And now we compare the formula, okay? So U is what? U is our delta G, right? So, sorry. Okay. So let me, the order of the term, yeah, maybe to match, let me write, yeah. I haven't been using this notes for 2 years, my bad. I should have tidied it maybe a long time ago. Sorry. Okay. Yeah, this is much better. So in this order. So we just compare the terms, all right? So
It wasn't the same thing. You just changed the position, I mean the orders.
yeah, they're the same thing.
So
It's
why-
just for you guys to better understand. Otherwise, you will get confused because we're using this term to match this term,
Okay.
and we're using this term to match this term. Okay.
Okay.
Same thing, but looks better, you know. Tidier. Okay. So now let's do it. Now let's do this term by term. So we have U is delta G. Okay. I mean, we replace delta G at the kth iteration by delta G. Okay. And this alpha. So what is alpha? So alpha is, if U is delta G, why am I writing this? This should be, my bad. This should be tensor product. Yeah, sorry. So then alpha is nothing but the denominator. So it's a number, okay? So it's a scalar. And then let's look at V. So V should be this guy. All right. So V is V delta X. And beta is negative V delta X delta X. This is also a scalar. So here is what we're going to do. First, we denote this part, okay? The first part is we have two rank 1 update, all right? We have two rank 1 update. The first one is B plus. This is a rank 1 update, okay? This is a rank 1 matrix. Then we have another rank 1 update. So what we're going to do is we use SMW twice. So with that, we denote right on bottom. No, we want to invert this first. So then, B plus equals A plus beta inverse B tensor product with V, so by Sherman, Morrison, Ubery, okay, we have B plus inverse, it's going to be A inverse, so we'll use this formula right here. So it's A plus beta inverse B and B, and this is subtract beta plus A inverse B inner product with V, and on top it is A inverse B tensor product with A inverse. So we should have, so what is, let's see, what is V? Okay. So if we look at what is V here, okay, then we're going to get so V is B times delta X, then we will have, this is beta plus A inverse B delta X, B delta X, and this is A inverse B delta X tensor product with A inverse B delta X. So the whole thing boils down to whether we can simplify A inverse B. The good thing about it is A is this guy. Okay. So all I want to do is we apply SMW formula. So we apply SMW. So we apply the Morrison, this Ubery identity on A again. So A is B plus alpha inverse U tensor product with U. So we apply this, we get A inverse is B inverse subtract alpha plus, so we have B U inner product with U and B inverse U tensor product with B inverse U. So let's remind us the following, that B and H, okay. So B is a symmetric matrix. So our update keeps the symmetry. And we start from a diagonal matrix that is symmetric. So H equals B inverse. It's symmetric as well. Okay. So now let's look at our formula. So we can simplify now. So for example, we replace everything. So we know that B inverse is H. So this is the idea is in this update rule, okay, like I said last time, in this update rule, H is always kept as BK's inverse, okay? But BK, but this path, this duality path is hidden. We never used it explicitly. So now what we have is, now this becomes H, subtract alpha plus H, what is U? U is delta G. Okay. This is H delta G, tensor product H delta G. Yeah, let me keep this B as B inverse. Oh, H is fine. So and then use this formula, okay? So here we used B inverse is H. Then use this formula, it's kind of, we can, so here in this formula one compute A inverse B. Okay, now we multiply B on the right to see what happens. Okay, so A inverse multiply with B, and we also want to know this quantity, right? Okay, so we multiply this on each term, so we'll have this is H B delta X, okay, minus, so let me write down, is using the form of 1 over alpha plus H delta G, so this is a number, and then we have, this is H delta G tensor product with H delta G, the matrix multiplication with B delta X. Again, the nice thing about U tensor product V X is nothing but, okay, so U V transpose X, but we can compute these two first. So now we apply this on this formula, right? So it becomes, so H so this guy, tensor product with this guy, and then matrix multiplication with this guy is nothing but, so H delta G, and this guy's transpose, times B delta X, and you will see where we're heading to, that is, so this becomes delta G transpose, okay, H transpose, so we take transpose of this matrix vector multiplication, and this B times delta X. H is a symmetric matrix. So H equals H transpose. Then, H transpose B is HB, which is identity matrix. Okay. So H is the inverse of B, B is the inverse of H, and they're both symmetric. And it can simplify lots of things. So we have this is H times delta G. Now this is delta G transpose. This is identity, so this is multiplied with delta X. Okay. We may want to keep this. Okay. So now, and we also want to use this here, right? So this is identity as well. So now what happens is, so this implies we have A inverse B, delta X is delta X, subtract. So this guy becomes this guy. And this can be further rewritten as H delta G. We group these two together. Okay. Thank you very much. So we group these two together. Okay. And we have this is minus alpha is this guy. Okay. So this is alpha. And then plus H delta G inner product with delta G. And on top, it is this guy, which is this. That is H. So let me reorder it a tiny bit. This is delta G, delta X, then times H delta G. Okay. All right. So we can rewrite. So we can rewrite this thing. So we make some simplification. So if we further let gamma. So here. So let's resolve this board. Okay. So we let gamma equals. If we look at this this term, so everything inner product is a scalar. So this whole thing is a scalar. Okay. So this whole thing is a scalar. So we let it to be gamma. So we let gamma to be delta G, delta X divided by delta G inner product with delta X plus H delta G inner product with delta G, and then this simplifies to this is delta X subtract gamma H delta G. So now what we want to do is we're almost there. So we have A inverse B delta X So we have A inverse B delta X, A inverse B delta X, and we also have A inverse B delta X here. And so we want to simplify the denominator first. So if we want to do it, so for example, the denominator, so let's call this equation B plus. So if B plus, what we want to do is we simplify the denominator. So A inverse B delta X times B delta X. This is then. We simply replace the first term with this. We'll have, this is delta X, subtract gamma, H delta G, B delta X. So now the interesting will happen. For this term, so I mean delta X, B delta X, we just write it as it is. So I mean because the symmetry of B, we can also revert these two, so it looks like our inner product. And for this term, so gamma is a number, so we have this as H delta G, B delta X. So the inner product of these two, okay, so let's have an identity here. So H delta G, B delta X is H delta G transpose times B delta X, which is delta G H transpose delta G transpose B delta X. This is identity. And then this becomes delta G transpose inner product, delta G transpose times delta X, so it's delta G inner product with delta X. Okay. So now this is simple. So now we're almost there. So the denominator here, the second term in B plus, that is beta plus this guy, that equals so what is beta? Beta is here, okay? So we'll find very similar term. So beta is, so this is beta, B delta X, but minus, okay? This we just computed, it is plus delta X, B delta X, and then multiply with this guy. But this guy we have is simple. It's minus gamma delta G delta X. So these two cancels. Okay. So these two cancels, what's left in the denominator is just this guy. Okay. All right. So now we have a, let's say, we have our B plus plus, this formula. And that is B plus inverse equals A inverse. A inverse is that. Okay. So this is our A inverse. And then we have this term. This term, what happens is, this is subtract. We have this whole thing. And the denominator is nothing but this guy. So what we have is, we have two minus signs. So we have a plus, and we have a gamma, but this is gamma inverse. Now let me keep gamma in the denominator. So this is our update formula, but not yet. Okay. So the last step is what? The last step is we simplify this guy, tensor product. So now let's look at our formula here. So by A inverse B delta x is delta x subtract gamma h delta g. Okay. I mean, so for the tensor product, we actually we have the same rule. So for example, it's u plus b tensor product with u plus b, all right? So we have, so this is actually analog of the simplest formula we learned, maybe even back in middle school. That is, this is a times a plus a times b plus b times a plus b times b, okay? It's just happened a times b is b times a. We can simplify this formula to be a squared plus 2ab plus b squared, okay? So now we don't, so this one doesn't have, this one is not commutative. So what we need to do is we keep, so unless, you know, certain things happen, but in general, we shouldn't. We shouldn't assume it's commutative, so we have this expansion. This is just a FOIL, I mean. The famous FOIL formula we learned in middle school. Okay. So now we'll apply this. Question?
No.
We're plugging this here, but we use that formula.
In the numerator, in the second term, it's A inverse B delta x or bx.
Thank you very much. Yes. Actually, when I wrote it, my mind was thinking, hey, did I mistakenly wrote x delta x as x anywhere throughout the course of the class? Then I mistakenly wrote it. My bad. Thank you very much. Okay. So now we're ready. Okay. Our one last simplification, and then we're done. Okay. Do the same thing. subtract, so this tensor product with that, we can pull out, the gamma is a number, so we have this is delta x, but we have to keep the order, okay. Tensor product with h delta g, and then subtract gamma h delta g, tensor product with delta x. And last term is a positive term, but it has gamma square, that is h delta g, tensor product with h delta g. So let's focus on which term? On this term. Okay. I think so alpha is that, right? So alpha is this. So let's focus on this term. Then we find, so if we plug in everything, there will be a term looking like, so gamma square h delta g, tensor product with h delta g, but divided by the denominator here, that is delta g delta x. So alpha is this, okay, and then there will be one cancellation. Why? That's a yeah. So that is h delta g, okay, so this is alpha, okay. There should be one cancellation. Let's still write everything explicitly, okay. Okay, so b plus e then becomes b plus, there should be some cancellation, let me see. So h subtract, oh, here we go, yeah, here we go. We let gamma equal this guy, okay? We let gamma equal this guy. This implies what? This implies, this is alpha, okay? This is alpha. So, this is alpha plus this guy. So it's alpha plus h delta g, yeah, maybe this is not visible. Let me write down here. So the denominator here, okay, so because gamma is delta g delta x plus h delta g, and on top it's delta g delta x. So this becomes, so this implies, this is alpha. Okay. This is alpha, so it implies the denominator of alpha, the denominator is alpha plus h delta g is equal to, we just divide this gamma on bottom, G delta X divided by gamma.
So why we don't change the numerator is also alpha in the up portion? I mean,
You can, I mean, of course you can.
Okay.
Yeah.
Because we don't need that, why we don't change it.
We just, so in the end, because the formula will be presented as delta G and delta X, so
Oh,
you can change it back anytime. Okay. Now we're back here, so B plus plus becomes B plus inverse equals H. Okay. Subtract that guy. But this will be this, so which tells us this will be delta G, delta X, and this is divided by this, and which puts gamma on top. Okay. All right. So the first term here becomes the first term. And now we expand the rest. Okay. Now we expand the rest, we will have, what we have here is plus delta X, tensor product, delta X divided by gamma, delta G, delta X. And then second term and third term are these two. So subtract gamma delta X tensor product with H delta G divided by gamma, this guy. Same thing. So this term is minus gamma H delta G tensor product with delta X divided by gamma delta G delta X. And lastly is we plus this term divided by this term square H delta G tensor product with H delta G divided by gamma delta G delta X. Okay. There will be one cancellation. And that cancellation is this term will be cancelled with this term. Okay. So now we're done. We've reached the update formula. So B plus inverse is just H plus. So H plus equals H, okay, plus gamma inverse the gamma here cancels. Gamma is some not so good term to compute. And we combine these two terms. How about that? This is our update rule. So let's remind us, H plus is our HK plus 1, and H is our HK, gamma is this guy, delta G is delta GK, and delta X is delta XK. That's it. This is our BFGS. Update rule. To use the duality and well, keep the rank 2 update. So so that's it for today. Okay. So next time we'll verify the properties of this, but it will be quick.
Thank you.
Yeah, let me keep the board here, just in case some of you, I don't think the next class they will use a board, they will use a projector, but let me keep it here, okay?
Hell.
What was that?
This is the rank 1.
Just like when the class becomes just like, without any numbers, you should be afraid.
Yeah.
I lost
Like,
100 times and lost the connection. What is doing that?
Just play with the number, just words like.
yeah, he just
you
like, just replace everything and plays everything with other stuff.
The problem is that he doesn't have the time to explain the motivation behind each step.
Exactly.
Why we would choose to make the choices that are being
Yeah,
made.
exactly, exactly.
Because he doesn't have time.
I sometimes say like his
Just-
spontaneousness. He is
See,
moving down
see,
there to there.
You sit here, I sit there. That's it.
To change the place.
Change the place.
Same class.
I'm just. Man, this is such a headache.
Really, it's really tough. First time I just recognize what he started, and I forgot. Then I needed to Google it.
Hello, how are you?
Do you have, okay, I'm talking with all of you. Do you have group study this week for exam?
Solo, I think.
Yeah, I don't have time for anything.
Oh, I see. Okay. So, maybe say that, so I was asked.
Anyway, I was talking on the Brit Skywalker or whatever.
Sorry,
No,
I think I took this study.
Like they all just they all needed your attention.
Man.